Okay, so we are going to learn about the density of a gas. I'll be honest, I tried to figure out how to play this video and it not have horrible feedback, but right now I'm having absolutely no luck. So I'm going to post this video. It was a demo that I was going to do, a little bit of a variation of this, and just can't get it to work yet without you being absolutely irritated with me. So I'm going to post the video. I want you to watch it later because the proof of this video is going to let you realize that different gases have different densities, and because carbon dioxide happens to be more dense than normal air and it has the property of being able to extinguish fire, we can see it have this effect with this video that you're going to watch. So make sure you watch it. But what we're looking at is density of a gas. And sorry for that. Whenever we solve these types of problems, some things that you need to consider are, and this is in your guided notes, the equation we're going to use is just normal density equation. So density equals mass divided by volume. Our units might look a little different than things that you are used to in physical science. We're going to be talking grams per liter because we're going to equate this around the density and the volume of gases. We'd probably be thinking grams per liter, but any mass per volume unit would be fine. And some stuff that we can apply with this. Now, everything you're going to see is equations that are listed on your reference sheet. But some things, we are only going to have you guys do this for density of a gas at standard temperature and pressure. Now, we could use ideal gas law and we could apply this in other situations, but for our sake, we're going to keep it at just STP. So I could calculate the density of a gas at STP easily by multiplying the molar mass by 22.4 liters per mole, because we know at STP, that would be the standard volume that any gas would have. Now, with this one, yours truly made some mistakes, but let's change it. So you could also calculate the molar mass if we know this. We're just manipulating the equation, and these are literally right on your reference sheet. But by multiplying or calculating the molar mass of a gas at STP by multiplying the density by 22.4 liters per mole again. So like I've told you before, sometimes we just need you to mark some stuff out. So if you would do that, that would be great. So what I'm going to do is run through, sorry about that, I'm going to run through all those examples that you have right there on your guided notes and talk you through how to do those problems. Okay, so we are going to do this problem first, where it just says to find the density of fluorine gas at STP. And as a reminder, on your reference sheet, we are looking at, it's the very last page, and it is this information right here. So what does density equal? We're going to use that equation, and then also it's just set for molar mass. So same equation, one set for density, one is set for molar mass. So those are the two equations that we're going to focus on. So we are being asked to find the density of fluorine at STP. So based off of that equation, density is going to equal the molar mass, and that's going to be multiplied by 1 mole over 22.4 liters. Okay, so if we think about fluorine, don't forget that it's diatomic, and so we're technically doing 19.00 times 2. So whenever we do that, we get 38 grams per mole. So I just want to show you why this works. So if our density equals molar mass, we have 38.00 grams per mole. And remember that density is really going to be a grams per liter. It's a mass per liter type of measurement. And we know this only is going to happen at STP, but we know at STP, 1 mole is going to occupy 22.4 liters. So that makes my mole unit cancel out. So I'm only left with my grams and my liter amount. So in this particular case, 38 divided by 22.4, I end up with 1.696 6, which I've afforded 3 significant figures, we would say, and I would really take 4 as well, because do we really count that 22.4, or should we let that limit us? So I would take either 3 or 4. So 1.696, and this would be 1.6964. I technically would expect this to be probably 4 sig figs, but like I said, I could see where you could also argue 3 significant figures. But technically, these are exact measurements, and we don't want to be limited by that, so we'll be limited by the molar mass that I gave you, which in this case had 4 significant figures. Okay. Okay, so this next problem is going to be a little bit more because we're having to find the density of each one of these, and then we have to actually rank them. Now, I'll be honest with you guys, I do not have the periodic table that I have shared with you that we've used all year. I have not been back to school yet with everything going on. And so if my molar masses are off, it's because I pulled them off the internet and I don't know exactly what we had on that sheet. So you're just going to have to forgive me. So if we look at carbon monoxide's molar mass, we would be adding 12.01 plus 16.00. And that ends up being 28.01. This is grams per mole. We multiply that by 1 mole would occupy 22.4 liters, and we get approximately 1.250 grams per liter for carbon dioxide. For C2H8, 2 times 12.01 plus 8 times 1.01, we end up with 32.10 grams per mole. Same operation. 1 mole, 22.4 liters. We get 1.433 grams per liter. To continue this, holy man, I don't know if I'm going to have enough room. B2H6. Boron is 10.81, so 2 times 10.81 plus 6 times 1.01. And I get 27.68 grams per mole multiplied by 1 mole, 22.4 liters, and I get 1.236 grams per mole. Then we need to do this for N2O. So we have 2 times 14.01 plus 16 . And I get 44.02 grams per mole multiplied by 1 over 22.4, 1.965. Then we get to do this for POF3. So that's going to be 30.97 plus 16 plus 3 times 19. I end up with 103.97 grams per mole multiplied by 1 mole over 22.4. I get 4.642. Grams per liter, and you guys can see I'm struggling with space here. Then we have hydrogen. So 2 times 1.01 multiplied by, and 1 mole, 22.4. Sorry, that should not have said grams per liter. That should have said grams per mole. We get 0.0917, and I'm running out of space, grams per liter. Okay, so increasing order. Holy man, I think I'm going to have to write this really small right here, but these are the numbers that we're looking at. That's a pain right there, huh? What teacher made these as your options? So increasing, looks like our lightest is hydrogen, which makes sense. And then from there, it looks like we have B2H6, then carbon monoxide. Then we have C2H8, that's our ethane. And then we have nitrogen dioxide. That is silo gas, kiddos. Talk to your dad if he's a kid of a farmer. He knows about that. And then we have POF3. So that is how I would answer this question. Okay, looks like I did not make sure that you could see everything. So there you go. Okay, for this one, we've been given the density of the gas, and we're kind of going in reverse order, trying to figure out, well, which molecule is it actually? So we're going to do the same idea. The density is 0.716 grams per liter. Well, we know that, and this again only works because of STP. There's 22.4 liters in 1 mole. So it's just a matter of canceling units. So we end up with 0.716 times 22.4, and we get 16.04. I'm just going to leave it like that for now, grams per mole. And the question is, well, which of these is it? So if it's H2SO4, or H2S, sorry, we want to know what its molar mass is. And that molar mass is going to be something like, oh crud, I forgot to look up its molar mass here. Something like that. Don't remember what that one is. But we already know it's not right. So 32 plus 2 times 1.01. So that's 34.02. So that has to be ruled out. It's not going to be this one. Carbon is, or methane, so 12.01 plus 4 times 1.01. This is looking a little more possible. So 12.01 plus 4 times 1.01 is 16.05. Wow, would you look at that? That is really looking like what it might be. But just to double check, well, what's oxygen? 2 times 16.00. Well, that is a molar mass of 32 grams per mole. So it can't be that one. So it must be methane gas. All right, and then let's go ahead and do this last one. So the molar mass of a gas is 20 grams per mole. What is its density? So again, just simple playing with conversions. If it's 20 grams per mole, well, we know that 1 mole is going to occupy 22.4 liters at STP, so 20 divided by 22.4, and we